Okay, Bismillahirrahmanirrahim. So inshallah today we will cover a new chapter, which is the transformer. Okay, I really hope that the previous chapter you can understand well and try to do the exercises, inshallah. Okay, so this chapter I believe is a common. Okay, we also learn this transformer, I think, in previous maybe in the school, okay, and also in the maybe in the foundation matriculation or diploma. Okay, so this is the outline, okay, for this chapter. Okay, so today class we will cover up to the 2.6, okay, so the equivalent circuit of a transformer. Some of maybe half of the equivalent circuit, so and the other I will give you the video and you will study only regarding the equivalent circuit, because the video is cover 6, 7, 8 and 9. So I want you to study the equivalent circuit only at the video. Okay, so yeah, the 1.0 is about the history. So again, please watch this video later. Okay. Oh, I forget. I never share this slide before. It's okay. After this, I will share. Okay. So this is the history.
Doktor.
Yes.
Doktor tak present.
Oh, lah lupa lah. Sekejap. Sorry. Terima kasih. Patutlah. Lupa lah. Shot sendiri je. Okay, boleh nampak?
Boleh, Doktor.
Boleh Doktor.
Sorry. Okay. So again, so this is the outlines for this chapter. So we have 9 subtopics for this chapter. Inshallah, we will cover up to 6, 2.6, the equivalent circuit, and the rest we will cover next week. Okay, don't worry. Maybe you see 1 to 6 is much, but actually it's simple. Okay, so later on please watch this video. So 2.1 actually is the history. I can say it's a history, why it's important. Okay, so yeah, this is due to the previous inventor, which is the Thomas Edison, and then they generate DC. Okay, wait, where is the, so they generate DC, and then they try to transmit. However, the transmission could not be transmit too far because of inefficient due to the high losses. Okay, and then they try to develop if I'm not mistaken, the Tesla, they develop AC current, and then they try to transmit. So they can see that the transmission losses is very small. It's small, okay, compared to the DC. So therefore the AC is important. So to transmit to one distribution center, okay, to from the plant, power plant, to the distribution, okay, up to our house, they required a converter, okay, some converter lah, which is the transformer. Okay, so the transformer allow or have less losses, reduce losses. Okay, later on you can read. This one is it's like a it's like a history. So this is also a video, so you can see. You can watch after this. Okay, please watch every detail or every video that I include in the slide. Please watch. Okay, so there are two types of transformer. Okay, so the name is the power transformer. So they constructed of one of two types. So the first one is the core type. Okay, so this is consists of a simple rectangular. Okay, dia macam rectangular lah, like this. Okay, so there is two winding. So this side, left side, and also right side. So this is core form. So the core actually there's a laminated. It's like many of layer of the plate. So the plate banyak, and then they combine, so become a core, so become a rectangular. So this is due to the eddy current, to reduce the eddy current. Okay, so laminated pieces of steel. Okay, kalau ada gambar, so this is the figure. So and then the shell type, so they consist of a 3 leg. Consists of 3 leg. So yeah, to simplify the winding, I can show you it's like up and down. It's like this. Okay, in and out. However, in the real situation, it's not up and down. It's dia macam ni, the atas bawah, they combine together. Okay, so you can see here, the primary is inside, the secondary is outside, or maybe the less power is inside. Okay, it's okay, nanti kita tengok. So this is, you can see the laminated banyak. Okay, there are consists of few plate, so become one core. So this is a transformer. You can see maybe this one is less than the other side. Okay, I believe the previous Nokia punya charger, the Nokia charger still using this kind of transformer. So nowadays they are using electronic unit. So this is at the distribution center. Okay, maybe TMB they are using shell type. Okay, so there are also consists of a few other transformer, which is the special purpose transformer. Okay, the special purpose transformer. So which are the potential transformer and also the current transformer. Okay, so potential transformer is sampling a high voltage and produce low secondary voltage. Okay, and also they can handle a small current. So the current transformer, actually they want to reduce, okay, a smaller secondary current. Okay, if you open the aircon, inverter aircon, inverter aircon in the outdoor unit, if I'm not mistaken, if outdoor board, outdoor board. So they consist of current transformer. They're using a current transformer. Okay, so later on you can try, because previously my aircon also break down, and once I open the board, I can see the current transformer is they call it as a open circuit. So open circuit mean there ada leakage, macam ada wire tu disconnect, they disconnect. So we need to change the current transformer. Okay, so this is a potential transformer in the distribution. Maybe this is not in TMB, but they're using there. This is a current transformer. It's very small. Yeah, this is very small. We use in the electronic board. Okay. Okay, now we go to the ideal transformer. So to get the general information about the transformer. So this is button. So yeah, even though in the real situation, there is no ideal transformer, but we need to study the ideal first. Okay, so later on, even though we will study the ideal, the real transformer, but we still use the equation from the ideal transformer. Okay, so an ideal transformer is a lossless device, okay, either in input or the output winding. So there are a few assumptions made for the ideal transformer. So yeah, the firstly is it is infinitely easy to set up a magnetic flux in the core. So alternatively, we could say that the core permeability is infinite. So previously, we can compare to the core to the we have a mu r, mu and also mu naught. Okay, so if we compare to the free space, last time we can see that there are up to 2000, okay, or maybe 6000. Okay, however, the ideal is up to infinity. Infinity macam ni. Okay, and then the reluctance of the core is 0. So what happens when the reluctance is 0 or the circuit? Kalau the circuit tu, kalau kita ada circuit power, bila resistor ni equal to 0, dia akan jadi apa? So it become like a short circuit. Okay, which is the current fully from here go through the resistor, still full value the current, and the magnetizing current required is almost 0. So later on we will see the magnetizing current. And then so this is lossless, meaning from here no magnetic flux leak. Okay, so between the winding so dekat winding tu, so the winding tu dia tak ada, there is no leakage there is no flux leakage. Okay, and then the winding resistance is 0, and also there is no hysteresis or eddy current power loss in the core. Okay, so yeah, I believe some of you mentioned why we need to see the eddy current in the transformer. So you need to know because once the flux go through flux kan go through dia lalu kan, bila flux go through the core, okay, the flow. Once the flux flow, they will induce a voltage, and the voltage will induce also the current, and the current katakan ni daripada side sini kan, kita cut, kita tengok sini and then dia punya flux go through macam ni kita cut from sini kita ambil sini. So when we use a right hand rule, okay, so the current will produce like this so the eddy current will produce circally okay, dah tak nampak dah. Okay, so flux dia akan produce macam ni lah eddy current tu. Okay, so bila ada current, when there is a current, they will induce a flux. Okay, so bila ada flux, so dia akan minus balik, dia akan tolak balik semula dengan flux yang sedia ada tadi tu. Okay, so dia flux lalu, they produce current, so current will induce the flux, the magnetic flux. So the original flux combine with the induced flux, so they will deduct each other. So sebab tu dia akan reduce, sebab tu dia ada loss. So kalau dia bertambah is okay. Okay, dia tak ambil kisah lah, tapi dia bertambah, so dia macam resistant lah sebenarnya. Okay, so later on you can see okay, so the ideal transformer, the relationship between the voltage, okay, the voltage Vp applied to the primary side, okay, and the voltage secondary side. So this is the transformer. where is this is the primary winding and this is the secondary winding. Okay, so this is the relationship. So the A is, they call it as a turn ratio, transformer turn ratio. Okay, transformer turn ratio, or turn ratio of transformer. So Vp minus Vs. So primary AP is stand from primary. So from here we can see that the primary is always for the voltage, the primary will be at the top, okay, and the secondary will be at the bottom. Okay, so top and also top, so they become A. So later on you will see the 1 over A. So for the current, okay, so please watch this video later. So this equation actually is not inside the book, but I try to figure out somewhere and try to they call it like mathematical equation. I try to solve. So actually this value, okay, this equation is come from here. Okay, if you still remember the Faraday's law. Okay, Faraday's law, where is the E equal to negative N the flux over dt. So the voltage will induce when there is a change in flux. Okay, so we assume that the flux in this equation in sine wave. Okay, we assume is in the sine wave, and then we use the Faraday's law. Okay, we try to simplify the equation. We try to differentiate. So when we differentiate, we will get this. Okay, so however in the power system they use the sine wave, the sine equation. So since they use sine, so we need to convert the cos with the negative here. Okay, so they will become sine omega t minus 90 degree, 90 degree over here. Okay, so this is the magnitude. Okay, so we take the magnitude, and then so we will use only the magnitude because the transformer actually there is no change in the phase or the angle. So we just take the magnitude. So this is the magnitude EP. So this one become EP. Okay. So why there is a root 2? Because we deal with the RMS value. Okay, RMS. So RMS voltage. So we get this. Okay. NP flux M omega. So divide by 2 pi. Okay. So this is the EP. So why root 2? Because of the RMS value. Okay. So actually we can make it simpler because we change the omega to 2 pi. This one we change to 2 pi f. So we can simplify. I think get 1.44 something. Okay, but it's okay. We can use, or we can write like this. Okay, and then we change. We also can use. Oh, mana gambar dia? So and then still you can see the VP and the induce. Okay, so we can say this is the voltage supply and EP is the induce. Okay, this is the induced voltage. So we can see from here that VP is equivalent to EP. Equivalent to EP due to ideal in a situation. Okay, and then we can use the same turn ratio like previously, which is the VP over VS to NP over NS equal to A. So we can use this. Okay. So this one is the relationship between the current IP flowing into the primary side and the current IS flowing out the secondary. Okay. So from here we can see the current we cannot directly like this. We cannot directly write I P I S equal to N P. It's not like this. Okay, ni salah. Okay, so we need to start from here. So N times with the I. Okay, who can say that what is this actually? N plus I, N plus multiple with I is equal to what?
Flux.
Flux lah. Salah. This one become macam F tu lah. Magnetomotive force, MMF. Okay. And I. Okay, so you can see that the force MMF from the left side is equivalent to the right side. Okay, and then we can rearrange, become like this. So for current, remember, for current is inverse from voltage. Okay, so please remember. So when we use the primary, is at the top. Okay, but for the A will be inverse. Okay, so in terms of phasor quantity, this equation so ini sama je lah. And then the phasor angle between VP and VS is the same. Ni yang penting ni. Okay, the phasor diagram, the angle is the same. And the phasor angle for I and IS, IP and IS also the same. So this means that the turn ratio affect the magnitude. So the current will only the calculation here is only will affect the magnitude only, not the angle. Okay. Kalau maybe we heard before about the power factor. Okay, power factor, the angle between the current and also voltage, they will for the real situation, but for the ideal will be the same. Okay, so they affect only the magnitude of the voltage and current, but not their angle. So how about the polarity? So polarity macam mana kita nak tahu kan? So come in and come out. Okay, you can imagine. So sometimes macam ni kan, and then yang macam ni kita pun tak tahu macam mana dia punya mana satu, adakah macam ni I ataupun macam ni, ataupun positif, negatif, or ni positif, negatif, or ni negatif, ni positif. Okay, so the polarity is how to know the polarity. Okay, so to know the polarity, maybe in the data sheet they use a dot identification. Okay, they call this as a dot identification. Dot identification. So for primary side, when there is a dot over there, so when there is a dot, okay, when there is a dot over there, it means that the current will flow into the transformer. So when there is a dot in the primary side, so the current will flow in. Okay, current will flow in. Okay, and this one become positive, and the other side which is the undot part become negative. Same goes to the, it's like from the side, primary side, current goes into. Okay, from the secondary side, the current flow outside. Okay, when there is a dot at the secondary side, it means that the current will flow out from the dot. Okay, and this one become positive, and the undot part, okay, this is the undot part, undot become negative. Okay, so in terms of the signal or transformer waveform, so they will become like this. Okay, this one due to the same polarity. You can say the same polarity. Okay, and there is no shift. There is no shift due to this one. Dia kata tadi no, not the angle. So what happen when the current flow is terbalik okay, when there is current flow, when this dot identification is inverse. So same goes here. This one is primary side, so current will go into it, and this one we need to see where is it. So here, so the current will flow out here. Okay, this is negative, this is negative. So so if we take the they call it multimeter or other things, if you put the positive here, normally we take the positive here and below we take the negative, so we will get this signal. Okay, so we will get this signal. It's like inverse okay, macam polarity tu you terbalik kan, dia akan jadi terbalik lah. Okay, boleh faham setakat ni?
Boleh.
Okay, so ni masih senang ni. Okay, so transformer. Okay, so in short I can say that in short, for the transformer in the ideal transformer, the power in the primary side and the power in the secondary side is the same. Okay, the same you kena ingat P in and P out will be the same. Okay, tapi of course dia ada calculation dia tersendiri kan. So this is the equation for the primary and this is the secondary. So since we know that the angle will be the same so theta P will be the same as a theta S. Okay, so the current and voltage are unaffected for the angle. Okay, so theta P and theta S will be the same. Okay, and also the power factor will be also the same. Same power factor. What is the equation for the power factor? Siapa boleh jawab? Power factor equal to what? Tak ada orang jawab. So, ataupun dia PF je lah. PF is equal to cos theta lah. Okay, is equal to cos theta. Okay. Alamak, ada conteng kat bawah ni. Okay, so replacing the turn ratio in the phasor out and equation. So bila kita tukarkan equation tu, kita boleh dapat ni lah, V in dengan V out kita gunakan macam mana nak tahu ni. Kita dah tahu tadi cos theta, kita dah tahu cos theta sama kan, P dengan cos theta S sama, so kita akan tulis cos theta je lah kan. And then kita ada conversion tadi, kita ada VP over VS equal to A. Okay, and also IP equal to IS equal to 1 over A. Okay, so we just replace dalam ni, kita replace ni, nanti kita akan dapat sama lah. Kita akan dapat this equation P in equal to P out. Okay, so same goes to the other power which is the reactive power and also the apparent power. So first question for today, for the revision, I want all of you to explain what is the power, real power, reactive power, and also the apparent power. Okay, so there are 3 types of power. So you can see, kalau boleh tengok kat sini, dia semua dia macam ni. Okay, so nanti you explain lah. Dia ada triangle ni, mana satu P, mana satu S, mana satu A. Okay, mana satu Q. Okay, so try find it. Okay, then we want to see about the yeah, we see the voltage, the current. So now we want to see the impedance. Okay, transformation through a transformer. So it is like impedance is like a resistor, resistance. Okay, it actually is referred to the load. So therefore the symbol will be the ZL. Okay, ZL. So ZL means that impedance for the load. Okay, so and the load actually is placed at the secondary side. Okay, remember that the load will be in the secondary side, of course, because that is the output. So the impedance of the device or an element is defined as a ratio of the phasor voltage, okay, across with current. So it's like VIR, macam Ohm's law, V equal to IR. Okay, so this one becomes Z. So ZL become VL over IL. So ni senang I think ni tak susah lah. Okay, and then yeah, so voltage, for the voltage V load actually will be the same as a for the ideal will be the same for the VS. Okay, and also same goes to the current. Current of course the same because they will be in series kan. So later on we see the circuit. So and then how to move the load. So the load is actually at the secondary side, but we want to refer or transfer the load to the primary side. Okay, so yeah, you can see that the apparent impedance of the primary circuit of a transformer is Z prime. They call it as a Z prime. It's not a Z but a Z prime. Okay, because the transfer. Okay, so macam ni ni transformer. Okay, so this is ni ada load. So this is ZL. So this is IS. So this is plus minus VS. Okay, and this is VP. Okay, IP. Okay, so this is the turn ratio. A is somewhere here. Okay, so they transfer the Z to primary side. Okay, once they transfer to primary side, so nanti kita tengok dekat dia punya apa nama ni, apa they call it, equivalent circuit. So at the equivalent circuit, so they will transfer everything from here to this side. So the calculation will become easier. Okay, so they call it as Z prime. So since the primary voltage and the primary circuit current can be expressed as the VP, ni yang tadi so turn ratio, and this is for current. Thus the apparent impedance of the primary is, so we just change the impedance tadi tu. Okay, so kita dah ada tadi tu, kita dah ada ni equation. So we convert this one to by using the current the ratio tadi. Okay, transformer turn ratio. Okay, so from here we replace from A. Okay, so we replace VP and then we replace to IS and then become this equation. So this equation is the Z. This is the ZL. Okay, so therefore this is the transformation. Yeah, the relationship between the for impedance at once we read at the secondary side or we read to the primary side. Okay, okay, so the easiest way to ni analysis kita nak analysis. Okay, so the easiest way to analyze the circuit for its voltage and current is to replace the portion of the circuit. Okay, replace the portion of the circuit on one side. So that's why tadi ada conversion tadi tu, of the transformer by a equivalent circuit. Nanti once kita dah masuk equivalent circuit tu, kita lebih nampak lah with the same terminal characteristic. So this process is known as referring. Okay, referring the first side of the transformer to the second side. Okay, so kita nak baca lah, tapi kena faham soalan tu, nanti kita kena faham either from the secondary side or either from the primary side. So sometimes they make confusion kat situ. Okay, for example here, here is from the primary side or the secondary side. Hello. Oh, ni kalau panggil nama ni mungkin tak ada ni. Okay, so this one at the primary side. Okay, equivalent circuit when the secondary impedance is transferred. Okay, transferred. Okay, so transferred to the primary side. Okay, and this one is equivalent circuit when the primary source is transferred to the secondary side. Okay, so kat situ kita boleh tengok lah. Ni sepatutnya ya, Z, this is Z kan, betul lah, AZ. Okay, so kenapa senang nak baca macam ni? So nanti kita dapat voltage. Once bila dah dapat voltage, kita boleh transfer kan, because sometimes we don't know the Z load. Okay, but we know the voltage, we know the current. Okay, this is known and this is known. The unknown parameter is the load or the impedance, the Z load. So we need to transfer to the primary side and then transfer back to the secondary side. Then we can get the value. Okay, from here we use Thevenin equivalent of the transformer circuit. So later on we will use the Thevenin equation. Okay. Okay, example 1. Okay, so from this example we will see more clear picture about the calculation. Okay, the equation is a single phase power system consists of a 480 volt 480 volt 60 hertz generator supplying a Z load. So this one is given, the Z load is given. Okay, through a transmission line of an impedance Z line. Okay, so answer the following question about the system. So there are two questions. So the first one is, if the power system exactly as described the figure A here, so what will the voltage at the load? Okay, voltage at the load will be, and what will be the transmission losses be? Okay, first of all they want to find the V load. Okay, and the second one the losses. Losses is equal to P equal to I square R. Okay, so the losses line. So of course this one will be the line, I line and R line. Okay. Okay. I believe this is very easy because this is a normal circuit. Okay, where we have the ZL and also we have a Z line. Okay, so from this circuit we can see that everything is in series. Okay, so since it's in series, so we can write the Z equivalent become Z line, Z load plus Z line. Okay, plus Z line. Okay, and then we can get the IG. So V equal to IR, right? Okay, so V is known, I is Z and so Z. So this is known, Z is known, I is unknown. So IG equal to V. Okay, V 40. This one divided by Z equivalent. Okay, then we can get the IG. So once we get the IG, so to get the V load is equal to I line at IG will be the same as a I line equivalent to I load. So this one is Ig become times with the Z load. So we will get the V load. Okay. So this is the calculation. Okay. So from here, since in series, so Ig equal to I load. Okay. So yeah, this is the Z equivalent. We combine all together, we will get the I line. Okay, this is the value of I line. So once we get the I line, to get the V load, just use the Ohm's law or something like the Ohm's law. So then we will get the this value, the voltage. Okay, please be remember. So once they mention, so in the equation they just mention voltage equal to 480 volt. Okay, so we need to remember that everything, when there is a voltage, they didn't give any angle, so means that the angle or the phasor angle for the voltage, okay, for the AC voltage is equal to 0. Become 0, starting from 0. Okay, so therefore become starting from 0 here. Okay, then we will calculate. So the easiest way to do the calculation by using your calculator. So you need to use the imaginary punya mode. Okay, so then the lines losses. So I line, this one, this is the line, transmission line. Okay, line Ig same to I load. So we just times here only. So we want to see the loss at the line. So the R line here. Okay, so we get the this one, this value. So then the second one, there is a transformer. Suppose 1 to 10 step up ratio is placed at the generator end of the transmission line, and 10 to 1 step down transformer is placed at the load. Okay, so this side is a macam power plant. Contoh power plant. So kita nak transmit, so we need to increase. Okay, we need to increase the voltage. Okay, first we need to increase first. So we increase first the voltage, and then bila this is the distribution line, and then bila nak sampai ke rumah, kita buat step down. We do a step down, okay, to the required voltage. Okay, so we increase first and then we step down. Same question. Okay, what will be the load voltage now? Okay, what will be the voltage now, and what will be the transmission line losses? Okay, so please remember, the first thing we need to calculate is the Ig. Okay, the current. The current. So the previously we can see that the circuit is all is in series. So now it's not. Okay, so how? Ada yang siapa boleh bagi gambaran? Siapa nama ni? Livinesh. Boleh bagi gambaran? How to calculate? Wah, ni kantul tak ada ni. Gabriel. Oh, Gabriel.
Ya, doktor.
So boleh bagi gambaran? Can you give the early information how to calculate? You have you can imagine how to calculate?
Doktor.
Okay, it's okay.
Belum.
It's okay.
Okay, doktor.
So yeah, since previously we know about the turn ratio, so we refer one side to the referring one side for the other side. So now we want to refer this load. We transfer first to the transmission line, and then we get the equivalent Z and then we transfer to the distribution or the power plant, okay, the generator side. Okay, so we need to do a 2 times macam transmission lah, bukan transmission, dia panggil apa, referring tu lah. Okay. Okay, first what we need to do actually, we need to eliminate the transformer T2. Okay, this one T2. We need to eliminate the T2, so will become like this, like a series between the load and also the transmission line. Okay, will become the series. Okay, and then we eliminate the second one, the first transformer, so that will become the series. They will become like this, they will become like this only. Okay, so how? Yeah, first kita dah tengok tadi kan tentang Z load yang ni. Okay, so how to transform the load to the primary side. Okay, mana tadi? Okay, so the value of the load impedance when referred to the transmission system voltage is, so dia punya, the A tadi adalah 10/1 lah. Okay, okay, so this is the equation. So when they write A here, okay, so we need to write the A/1. Okay, so kita boleh gunakan ni lah. Okay, V ataupun N kan, NP over NS equal to A kan. So okay, so sekejap ni terbalik. Oh, betul. Okay, 10/1 Okay, and then try to simplify, will become like this 400 ohm plus J 300 So then we need to combine together with the load from the line. Okay, so we need to add this one. These two we need to combine. So then will become Z equivalent. Okay, Z line plus Z prime. Okay, so we just add on both of these. Okay, once we add on, we need to refer back. We need to refer to the primary, or to eliminate the primary punya subhanallah, the transformer. Okay, so the total impedance at the transmission line, Z line plus Z load, is now reflected to the T1 transformer 1, to the source of the voltage. Okay, so then become Z equivalent prime. Z equivalent prime is equal like this. So the equation is the same. The equation is still the same. Okay, equation still the same. Okay, so Z L prime equal to A square Z L. Okay, so we try to simplify, and then we will get this value. Okay, so once we get everything in series, so then we will calculate the IG. Okay, so then we will calculate the IG. So IG is this value. If we compare to the previous one, IG is quite the same. 90.8. This one is more higher. Okay, once we get the IG, we need to transfer back the current voltage. Okay, so we can get the Z line and I load. So we use the turn ratio. Okay, so this is the equation from IG to I line. So we will get the I line, and then working with the, so once we get the I line, we can get the I load. Okay, so we get the I load. Okay, oh salah ni, ni tulis salah ni. Oh, ni ada salah sikit. Okay, ni salah. Not this one. Okay, it should be I load. Actually, is equal to mana ni? Wait, nanti sama lah. 5.94 negative 36.88 degree. So sama lah sebenarnya. Okay. Okay, they will get the same value. Actually, it's because of the conversion only. Okay. Because the turn ratio is the same. Okay, for the transformer 1 and also the transformer 2. Okay, dia satu dia naikkan 10, dia darab 10, lepas tu dia tolak balik, dia divide balik 10, darab 10 and then divide 10. So will be the same as the IG ya, IG. Oh, okay. So now it's possible to get the answer. So first they want to I load and V load. Okay, so just use the Ohm's law again. Okay, so we get the V load. Okay, and then the loss in the line. Okay, so from here we can see that the loss by using a transformer is more or less is lesser than without using the transformer. Okay, you can see here, tak payahlah, jauh sangat nak patah balik. Okay, so before this P loss is equal to 1484. Okay, so you can compare the loss. Okay, so it's very high. Okay, so now we're going to enter the real transformer, theory of the operation of the real single phase transformer. Okay, before that, can we take a rest for a while? 5 minutes. Is it okay?
Okay.
So we continue 3:16 Boleh 3:16. 5 minit
Boleh
okay?
Okay.
Okay, thank you.